previous two lectures, we obtained expression for Landé G factor and the magnetic susceptibility of solid systems consisting of atoms, and we considered that each atom itself develops a magnetic moment that altogether put all together give a net magnetic moment to the solid, and we assume that there is no interaction between the atoms. In this, a quantity that we considered was the Landé G factor, or simply the G factor, which was given as G equals 3 j plus 1 plus s plus 1 minus L plus 1 divided by 2 j plus 1, which is also equal to 1 plus j plus 1 plus s plus 1 minus L plus 1 divided by 2 j plus 1. And the quantities S, L and J are: S is the total spin of the electrons, L is the total angular momentum, which is due to the orbital motion, orbital angular momentum of electrons, and J is total angular momentum, which comes from the sum of L and S. In this lecture, we consider how for an atom the quantities L, S and J are calculated. So, let us see, when I have an atom, it has electrons in states N, L and M, and then I can write Ms, where N is the orbital quantum number, L is the angular momentum, quantum number, M is the Z component quantum number of L quantum number, and Ms is the Z component of spin of electron, which can be either 1/2 in units of h cross or minus a half. Now, a state NLM, that is only the orbital part, can accommodate two L plus 1 times 2, where the second 2 comes due to spin, and this is 2 L plus 1 independent ml values. These are from ml equals minus L plus 1 and so on all the way up to L. So, it can accommodate 2 L plus 1 times 2 number of electrons. So, we can write maximum number of electrons in NLM is equal to 2 times 2L plus 1. For example, consider carbon atom, which has the electronic configuration 1s2, 2s2, 2p2. So, if I make these orbitals as these boxes, this is 1s, 2s, 2p with the correspondence ml equals 1, ml equals 0, and ml equals minus 1. Then the maximum number of electrons that can come in 1s are 2, one with the spin plus half, the other with the spin minus half, which I indicate by these arrows. So, let me also write it here. This indicates ms equals plus 1 half, and the down arrow indicates ms equals minus a half. Similarly, in 2s also I can have 2 electrons, and 3s the maximum number of electrons are 2L plus 1, which in this case is 3, and 2 times 2L plus 1 therefore is 6. So, it can have maximum 6 number of electrons, but there are only 2 electrons. How do we fill these? So, this filling of 2 electrons here is to be done following something called the Hund's rules, and that is what I am going to state now. Before I state those and take up this example again, let me just make it clear that for a fully filled orbital, that is one that carries 2 times 2L plus 1 electrons, the L value comes out to be 0, because you are filling plus ml and corresponding minus ml. And similarly, all the electrons that are filled, half of them have spin ms equals plus half, and the other half has minus half. So, that also adds up to 0, and therefore, the S value is also 0, and the J value therefore also is 0. So, fully filled orbitals are no problem. We are more concerned with the orbitals where number of electrons may not be completely filling the orbitals. So, rule number 1 is that we fill all the orbitals keeping all electrons first in plus half state and then in minus half state. It will be clear as I take up the examples, and this is done in order to maximize the capital S value. And how do we start filling? We start filling with largest ml value, and then keeping the electron spin up, we go to the next ml and so on, and fill ml minus 1, ml minus 2, etc., keeping up spin electrons in them. Once they are filled, that means 2l plus 1 electrons are filled, we start all over again. So, after filling 2l plus electrons, we come back. To largest ml and start filling minus half spin electrons. So, this is done very systematically. For example, so again we are still in rule 1. In the carbon system, when I had 1s orbital, 2s orbital and 2p orbitals with 3 ml states, 1s, 2s, 2p. 1s and 2s are lower in energy. So, I will fill the first electron with up spin, and the next electron would not go to the higher level, it will remain in the same level, but will be with the down spin. In the next orbital also the same thing, up spin and then the down spin. In 2p, I have only 2 electrons. So, I will first fill the largest ml value with the up spin. The next also I want to maximize summation over ms. So, next electron will go with up spin in ml equals 0, and that is it, I have exhausted them all. If on the other hand I had oxygen, which has the configuration 1s2, 2s2, 2p4, in that case the way I will fill these orbitals will be again 1s, 2s and 2p. I am not writing now ml equals 1, 0 and minus 1, it is understood. So, I will first fill up electron in 1s and down in this is 1s. In the 2s, I will fill the up electron first and then the down electron, and in 2p, I will first fill the up electron in ml equals 1, then in ml equals 0, then in ml equals minus 1. I have tried to maximize ms as summation of ms as much as possible. Now, next electron, up electron cannot go anywhere in these 3 orbitals. So, I have to fill the down electrons, but I start all over again to the maximum value of ml and put the fourth one down here. This will be the configuration for oxygen. So, I have given you 2 examples where the number of electrons is either larger than 2l plus 1, that is a half filled orbital, or smaller than half filled orbital, and how to fill these electrons. Of course, if I have something in between, for example, nitrogen, which has 1s2, 2s2 and 2p3 electrons, the 2p orbital, 1s, 2s are filled just like we showed earlier, the 2p orbital will be half filled. So, in this case the 2p orbital will have only up spin electrons. So, this is how we fill the electrons. After we fill them, how do I calculate the m and s values? So, in rule number 1, we maximized summation ms by filling up electrons first, so that I can get largest possible value of ms. And side by side, I also did one more thing. We also maximized summation m l, keeping in mind that summation ms is first maximized. Let me explain that. We first put all the up spin electrons so that ms is maximized. Then only I took care of ml. So, for example, when I fill the carbon atom, I had 1s, 2s, and these are filled orbitals. So, I do not really discuss them anymore. These have ms and the L and s values to be 0. And when I come to the 3 2p orbitals, the first electron went with up spin to ml equals 1. Let me write this, ml equals 1, 0 and minus 1. Now, first thing I wanted to do was maximize ms, and therefore, I will put only up spin electrons first. However, an up spin electron cannot go here, this I will cut. It cannot go here by Pauli's exclusion principle, because no two electrons can have all the spins the same, and therefore, I put it in the next available ml, but keeping summation ml to be maximum. So, I cannot put it in ml equals minus 1, I will put it in ml equals 0. Similarly, in the oxygen atom, the first two orbitals are filled anyway. So, I do not really bring them into the discussion. The last 2p orbital, I first put first electron in ml equals 1, then I want to maximize ms first. So, I will put this in ml equals 0, again keeping in mind that I should maximize summation ml. And the next one again I want to maximize ms. So, I will put only the up spin electron. So, it has to go into ml equals minus 1. I cannot suddenly put a down electron in ml equals 1. So, that ml is maximized, but ms is not, and then I will put the down electron in ml equals 1 again. Once I fill it like this, then the s value is given as summation ms, and the L value is given as summation ml. And let me now show these values for the carbon atom and the oxygen atom both. For the carbon atom, the s value would be equal to 1, 1 half plus 1 half, and the L value will be equal to 1 plus 0, 1. Similarly, for the oxygen atom, the s value would be equal to s equals 1, because the first two up and down electrons cancel their spin, and the other two give you s equals 1, and the ml value adds up to 2 times 1 plus 0 plus minus 1. So, this comes out to be L equals 1 again. So, that is rule number 2, how we fill the orbitals and then calculate the capital S and capital L values. These of course, are related to the total spin angular momentum and the orbital angular momentum. Next, rule number 3. This concerned with the J value, because remember, from quantum mechanics I know if we combine L and S, add them, then the possible J values are from L minus S mod to L minus S plus 1 and so on, all the values differing by 1 to L plus S. Thus, for example, if I have S equals 1 and L equals 1, I can have J equals 0, 1 and 2. And the question is, which J value corresponds to the ground state, because all these 3 J values are differing in energies. This has again been calculated and then given in the form of the rule number 3, and it says that the J for ground state is equal to mod L minus S if the orbitals are less than half filled. And that means that if number of electrons is less than 2 L plus 1, then J equals mod L minus S. On the other hand, J for the ground state is equal to L plus S if the orbitals are more than half filled, which implies that if number of electrons is greater than 2 L plus 1, J equals L plus S. And then for half filled orbitals, L anyway comes out to be 0 because the same number of plus and minus values of ml, and J equals S. So, this is rule number 3. So, we have given 3 rules that give you the values for J, L and S. And the way the ground state is represented, so let me write this clearly, the way the ground state, or for that matter any state, is represented in symbols is that you write 2s plus 1 value, then the symbol corresponding to the L value and J value here. So, let me now take examples. Carbon, we had 1s, 2s and 2p. I did not really worry about 1s and 2s because they are filled orbitals, and therefore, I do not really get any L or S values from there, they are 0. And the last orbital was like this. So, in this case, we found that the S value was 1 and L value was 1. So, L equals 1 corresponds to P, and now we are going to write capital P symbol for this. 2s plus 1 is 3, and therefore, I write 3 on left top, and J value, now this is less than half filled orbital. So, J value is going to be the L minus S value. So, this is going to be 3p 0. On the other hand, for oxygen, I am going to have one S completely filled and the 2s completely filled and 2p orbital like this, and here also we had obtained S equals 1, L equals 1. So, again it is a P state. However, the J value corresponding to the ground state is going to be now L plus S because it is more than half filled. So, it is going to be 3p2. If you wonder where these rules came from, these are done by calculating total energies of these electrons, taking their interaction into account. And last example I had done last time in the previous slides was that of nitrogen. So, let me do that also. And nitrogen had 7 electrons. So, I have these up electrons, and 1s and 2s have these down electrons also. Now, this is half filled. So, you can see that S comes out to be 3 halves, L value is 0. So, this is going to be corresponding to L equals 0. 2s plus 1 gives me 4, and J value is only S. So, this is 4s 3 by 2. So, this is what explains these rules to you, let me take some examples that are directly concerned with magnetic systems. So, let me take examples for lanthanides which are concerned directly with magnetic systems. So, first example I am going to take is that of neodymium, represented as Nd. In the solid, it comes in the state of Nd3 plus, and that gives rise to paramagnetism, and its electronic configuration is 4f3 5s2 and 5p6. You can see that 5s2 and 5p6 orbitals are completely filled, and so are the lower orbitals. They are going to give L equals total L equals 0, total S equals 0. So, we are concerned only with the F state. F state as is SPDF. So, F state corresponds to L equals 3. So, it is going to have ml values 7 of those 1, 2, 3, 4, 5, 6 and 7. So, this is ml values of 3, 2, 1, 0, minus 1, minus 2 and minus 3, and I have 3 electrons in this. So, all 3 are going to go starting with the highest ml value. I put an upspin electron. Since I am maximizing ms first, I still put upspin electrons, keeping in mind that I still have to have maximum summation over ml. So, it goes to ml equals 2 and the next one goes to ml equals 1. So, I have applied rules number 1 and 2. Now, the S value is going to be equal to summation ms, and this gives me 3 halves. L value is going to be 3 plus 2 plus 1, which is 6, and combining these two, the J value is going to come out to be, this is less than half filled. So, it is going to be 6 minus 3 by 2, which gives me 9 by 2. So, this state is going to be denoted by SPDFGHI. So, this has corresponding symbol I. So, 2s plus 1 Lj will be equivalent to 2s plus 1 gives me 4, L is equal to 6, that corresponds to I, and J value is 9 by 2. Let me take another example which is more than half filled, and this is homium. Denoted as HO, and this also occurs in the solid in 3 plus states, and HO3 plus has the electronic configuration 4f10 5s2 5p6. So, again if I make the f orbital L equals 3, I have 7 boxes corresponds to ml value of 3, 2, 1, 0, minus 1, minus 2, minus 3, and I have to put 10 electrons in it. So, first I exhaust all the up electrons, maximizing summation ms. Right now, I do not really care about ml, but I am taking care of that by filling ml values largest to lower values. Now, I exhausted 7 electrons. So, next 3 will go as downspin electrons in the largest ml possible values. So, S, which is given as summation ms, is going to be 7 times 1 half minus 3 times 1 half. So, that becomes 2. The L value is going to be summation ml, and that is going to be 3 plus 2 plus 1. All the others cancel out, and this is going to be 6. The J value for the ground state is going to be, this time is more than half filled. So, it is going to be 6 plus 2 L plus S, which is going to be 8, and therefore, the term symbol for this, which is 2s plus 1 L j is going to be 5, L equals 6 corresponds to I, j is 8. So, I have given you rules for filling orbitals with electrons, and that determines L, S and J values. These rules are known as Hund's rules. And once we know L, S and J values, we can calculate the Landé-G factor G as 3 J, J plus 1 plus S, S plus 1 minus L, L plus 1 divided by 2 J, J plus 1. Incidentally, the value square root of G, J, J plus 1 is known as effective magneton number. Why I will come back to this again. So, using Hund's rules, we can fill these orbitals and get the effective magneton number. So, to conclude, we have learned about Hund's rules and seen through examples how they are applied to determine L, S and J. Thank you.